about in a preprint on the archive. I was trying to send the link into the chat, but I failed, and I didn't write it on the slides. But you can look it up, and then some more is work in progress, yeah. So, anyways, let's go ahead. So, my talk is going to have 3 parts to it. Part 1 is going to be what. Part 2, why, and part 3 is how. I'm going to spend most of the talk on parts 1 and 2, leaving aside most of the technical details, but, I don't know, with my luck with these slides, I'll finish in like 10 minutes and then I'll be forced to tell you how. So we'll just see how it goes. I'll try to pace things well. All right, so let me start by just giving you the lay of the land about what the objects are of interest, what we're going to be looking at. So the basic setting is the world of semi-global fields, their models, and their various completions that arise on these models. The kind of main players are torsors for linear algebraic groups. And what we're going to be interested in describing are local global principles for these torsors over semi-global fields and what the obstructions are for these local global principles. So let me kind of go through and say a bit about each of these in turn, just so that I can set up and state the main results. So first off, semi-global field. So semi-global field, it just means it's the function field of a curve over a complete discretely valued field. And the kind of typical thing that you should keep in mind is something like function field over the p-adic numbers. Now, we don't have to have the complete discretely valued field be QP. It can be really any field which is complete with respect to a discrete valuation, and it doesn't have to be just, totally purely transcendental thing. It could be, some interesting curve, etc. That's kind of a good thing to keep in mind, though. And then, okay, so what's a model of a semi-global field? Well, if we have some semi-global field, think of it as function field of some x over some complete discretely valued field k. And what then you can do is find a relative curve. So a scheme which is defined over the ring of integers such that you want the generic fiber to be your x. You want it to be a two-dimensional regular scheme, which you can always desingularize this thing by Lippmann's result. And then we're also going to want the reduced closed fiber. So you take this thing, you look at it at the residue field of the valuation ring. You got some curve over the value over the residue of the valuation ring, and this should have simple normal crossings. So so just some nodal singularities and some components bumping into each other in these nodes. Okay, so that's what we mean when we say a model of a semi-global field. So we'll call this script x a model of f, and we'll refer to this thing as the reduced closed fiber. Okay, so it's like I'm writing, but I'm not writing. Okay. Okay, so a lot of the kind of statements of the result are going to depend on kind of combinatorial properties of the reduced closed fiber. So we'll say a few words about the structure of the reduced closed fiber. So first, here's a picture of a model of a semi-global field. We imagine that there's the spectrum of our DVR downstairs, which is like, kind of a fat, kind of a, I don't know, like a big point with a little point inside of it. And then over that, we have our two-dimensional scheme. From that, we can look at the closed fiber. Let's say it has these two components, x1 and x2, intersecting on some node P. And from that, we can construct a graph called the reduction graph. So the vertices of this graph are these components and the nodes. And we draw an edge to represent incidences. Okay, so for a more interesting example, let's suppose we have this complicated thing in our closed fiber, then we're going to have in our reduction graph vertices for each of these components and for each of these nodes. So you can see, for example, here at P, because there's one component X that kind of hits P twice. So formally, that prime that defines X breaks up into two primes in the complete local ring at P. And these are represented by these two connections instead of one. And you can see this triangle over here. We still have a cycle in the reduction graph coming from this triangle, but it's kind of turned into a hexagon because we've really like subdivided, some of these, some of these connections, these points really turn into edges. And so it's, anyways, okay. So that's the picture of what the reduced closed fiber looks like, the reduction graph, excuse me. We're going to need to kind of put some extra decoration on the reduction graph, though, to state the results. So there's also a kind of orientation that you can imagine to this thing. So we can kind of think of an oriented version of this. So how does that work? Well, if you give me one of the components, there's some field of definition of the component. So like these components, we're I guess I forgot to say like projective or proper back then, which I should have said. But, so if let's say everything is projective, the kind of global field of constants is some finite extension of our residue field, and we're going to call that kappa of xi. Similarly, we can look at the residue fields of the points, and in this way, you can associate fields to each of these vertices in the reduction graph. And you can also see that if a point lies on a component, its field of definition has to be at least as big as the component, because those are the constants on the component. And so, but when it's strictly bigger, you make a direction on that edge to go from the point to the component. So just for example, if they're both proper, you've got something that looks like that. If equality, we just call it undirected, and then, might have whatever. Okay, really too many drawings to represent something, but, the point is we're orienting some edges, but we're not orienting all of the edges. So, okay. And then the main property to state the result is this notion of a monotonic tree. So when the reduction graph turns out to be a monotonic tree, we get some extra results. What is a monotonic tree? So, well, it should be a tree. And there should be a directed route. So you start with some marking, some vertex, and you should be able to get anywhere else without going like against the flow of traffic, without crossing an arrow in the wrong way. And if you can do that, you call the thing a monotonic tree. Okay. So now, I can almost, now we have like part of the nouns necessary to state the result, but we need a few more nouns and adjectives. So now we should talk about completions of these semi-global fields. So suppose you have a model of a semi-global field. If you grab some point of codimension 1 on your model, then corresponding to that, some discrete valuation. You can look at the complete local ring and its fraction field. And these give you various extension fields of F. And in some sense, they're simpler because, complete discretely valued fields are always easier than before you completed them. And so the motivating question is, can we study our field by studying these simpler fields? Okay. So we're still in what? Sorry for the long what, but we're kind of in part 3 of what now, which is like the things, the kind of these, no, we're in part 2. I can't remember. Okay. Well, the main players, the objects of study that we care about are these things called torsors. I'm not going to like give a long talk about torsors, except I'm just going to say that we like them. We're interested in them. They're classified by this Galois cohomology group. And, we all like torsors. That's why we're here, basically, right? Okay. Um, and, and for the, for people who are new, it's good to just point out that these are in bijection with familiar algebraic structures of various kinds that we like. And that's one big reason that we care. And that's all I'm going to say. But there we go. Okay. So what's the main theorem? The statement is, suppose you have, so one of our results is, suppose you have a linear algebraic group over the ring of the valuation ring of a complete local ring, where then you have some semi-global field built over this. And suppose that you have I said directed tree, I meant to say monotonic tree. Sorry, you have a monotonic tree. Then this map the kernel of this is trivial. In other words, you can describe whether or not one of these torsos is trivial if you know that it's locally trivial, if, well, one of the following two things holds. So either G is an algebraic torus, or G is, I almost forgot, connected, reductive, and the closed fibers are geometrically reduced. Actually, I'm not sure if I really needed to say, no, I put too much there. I didn't really need that. Not geometrically reduced, just okay, well, fortunately, that's the part that isn't written down, so I can't contradict anything that's on the preprint server already. What I have here is a little bit too weak, and I forgot to, yeah. So sorry, that's too strong. We want, I guess, I don't know, David, for example, or Julia, we need the components not to have inseparable extensions in their constants. Is that a problem? I can't remember. Or David, your mic is off.
Yeah, well, the thing is, you're assuming it's monotonic, right? I mean, we said,
yeah,
because we said that, right, that was equivalent to geometrically a tree together with the separability condition. So
I'm just wondering what we need as the input into the other result. But actually, okay, let me just sidestep it for, I guess.
We need at least one component to be rational, multiplicity 1.
Okay.
That's a
so that's sufficient. So if it's a monotonic tree, and if one of the components is rational with multiplicity,
yeah, if it is k, yeah, with multiplicity 1.
Okay.
Not rational, but with multiplicity 1, and the field of constants is k itself or suburban.
Right.
Just
okay. Is reduced, and some mild conditions.
Okay.
Okay. Okay. And now how do I get back to my presentation? Okay, there it is. Okay. So, please feel free to interrupt me with whatever other questions and comments, even if you're not one of the co-authors. You're welcome to bother me at any point in the talk. Okay. So, for the more general statement, suppose you just can look at the pointed kernel of this map and just consider what torsors become trivial over all the completions. And so we can say something more specific in the case where the closed fiber is reduced and is just a union of P1s over the field. So this is a nice way to kind of construct examples where you can compute this obstruction explicitly. And in this case, the answer is kind of interesting. The locally trivial but not globally trivial torsors exactly correspond to kind of the combinatorial, topological H1, right? Just the H1 of the kind of underlying graph, so to speak, with coefficients in G of K mod R in the case that G is an algebraic torus. And similarly, we expect a similar statement in the reductive case, which is in process of being written. So this is, just the kind of combinatorial, let's say simplicial cohomology of the graph. So what does this say? This says that, if, for example, you get non-trivial but locally trivial torsors just from loops in the graph and loops combined with non-rationality of the group. So I'm sorry, I should have emphasized, this is G of K mod R equivalence. So so here, you call 2 points R equivalent if they're connected by a rational curve, Okay. So this is interesting. It's just saying that the obstruction to triviality has something to a local global principle, has something to do both with loops in the closed fiber and with rationality of the group. Okay, so why would you care to have these results? Why did we want to ask this question? Maybe that would have been a good thing to start with this. Like, why do we care? Torsors are really important for understanding field arithmetic. And on the one hand, you have fields like number fields, where torsors are, let's just say, quote unquote, well understood, and provide a useful perspective for understanding various kind of questions about the arithmetic of Q. On the other hand, way out in the distance, there's the holy grail, which is function fields over number fields. If we understood torsors over these things, we could do amazing things. We'd be able to, I don't know, say something sensible about Tate-Shafarevich groups and as they appear in arithmetic, and and so many other great things. Okay, but where we are is right here. So these semi-global fields are somewhere in the middle on our long approach towards these more general finitely generated fields over here. These are tractable because we now have techniques such as field patching and things like that to work with them. But they still have a fairly rich structure. They're able to exhibit a lot of the phenomena that we expect to find over here, maybe not all of it, but they're kind of clearly on approach to this other world. Okay. So now, if we've established that we care about these fields, how is it helpful to know about structures over completions? Why is that a good thing? Well, in general, when you look at these completions, these are, these are discretely valued fields whose residue fields are things like this. I'm just looking at QP of X as an analogy, right? You get residue fields like this, and there are so many techniques that tell you how to go from a complete field to its residue field. And there's a lot of roadblocks there as well, but still, that's like, something hopeful. And so the fact that we can deal with these residue fields and we can do kind of complete fields if we understand their residue fields gives us much more of a toehold on these various completions than for this. So whenever we can say that results about here can be reduced to here, this is kind of saying a lot about understanding the arithmetic over here. Okay. That's the end of part 2, actually. So so we're into part 3. Oh, this is what I was afraid of, I guess. The slides are so fast, and now I'm only 20 minutes in. Okay. All right. So I better slow down, but here we are in part 3, which is how. Okay. So I had prepared a brief patching kind of pep talk, which I think I might do, like, kind of extend beyond my slide, just so that, because what I was going to do was I was going to like motivate patching without actually telling you what patching is. but maybe I'll actually like define a couple of things instead as they'll be useful. Yeah, well, I'll probably add some stuff there. Okay, and then I'm going to give you just an overview of the torus results and what kind of things are different about the reductive group case, more general reductive group case. All right, so so unfortunately the animation part is over now, so I have to like use the little pointer thing. Okay, so let me now say a little bit about the yeah, I know what I could. Okay, let me just go on with this slide, I guess. Yeah. Okay, so let me say a little bit about motivating patching. So I should say though, this is not what we're actually doing. So what I'm going to say is not actually patching, but it's just the motivation for patching. Okay, it's kind of an interesting statement, I think, in itself. So let's just imagine we have a compact Riemann surface and we look at its meromorphic functions. Okay, so we're now kind of just in some other world for a moment. A natural question you could ask is, how can we construct objects locally on S to get objects over the field of meromorphic functions? So, you know, what we would like to do is somehow use the fact that we understand that there's geometry in S in order to understand this field of meromorphic functions. And, you know, and it's clear that you can't do this by going Zariski locally somehow. I mean, because, you know, you go Zariski locally on S and the functions don't change, the regular functions don't change. But when you, if you were to look at functions that are meromorphic on standard open sets, then, you know, you get some really interesting bigger fields going on there. And furthermore, you know, these, you know, there's these things kind of fit together and give a picture that's kind of like looking at, you know, almost like looking at completions at points if you kind of take limits of these things. And that's encapsulated in the fact that when you take limits over these guys, you get something that's maybe not complete, but it's Henselian, and its completion is the normal complete local ring at these points. So, so it turns out that that you can construct algebraic objects over fields of meromorphic functions of this type by looking at kind of local meromorphic functions on various open sets and gluing these things together by the kind of combinatorics of how your open cover fits together. So if somebody gives you an open cover, you know, if you have some open cover, a bunch of UIs, and you have some algebraic objects of some type over UI, I shouldn't say over UI, I should say over the meromorphic functions on UI. And if you have some agreements on these guys, when you restrict to meromorphic functions on UI intersect UJ to AJ, restricted to meromorphic functions on UI intersect UJ, such that they satisfy the cocycle condition, that they're kind of a compatible bunch of gluings, then you can glue these together to get an algebraic object over the field of meromorphic functions on your whole space. So this is a kind of a version of patching, and you can, I think if you're clever, you can go from this to some sort of a kind of combinatorial local global-ish kind of principle thing. Not exactly, I mean, maybe that's a local global is too strong a word, but you can kind of describe algebraic structures by getting things fairly close to completions using this kind of Henselian observation in the previous slide. Okay, I'm maybe not going to really justify the rest of that too much because, well, as I said before, this isn't actually what we're doing. This is just supposed to be an analogy. What we're actually doing is we're, and now how do I, okay, I'm now gonna like mess myself up for just a second so that I can, wait, okay, sorry, one second. Don't look. Where was I? Where was I? You're not looking, right? Okay, almost there. Need to add a slide. Okay, so what we're actually, yeah, I can put this. Somehow I knew something like this would happen. I lost my place. No, that's okay. I think I just killed something, but so I'm gonna go to my other thing instead. Okay. Sorry, I think I just killed it. Okay, so maybe I'll find that the final slides with results on them in just a moment. Okay, so so the actual patching that we're doing is, instead of having a Riemann surface, of course, we have some semi-global field, which we imagine is coming from some model over some ring of integers. We imagine we have some closed fiber, which I'll write like this. So here, this represents the residue field. And then what one can do, kind of along this route, is instead of thinking about meromorphic functions, you can think about a formal analog of meromorphic functions. So if you give me some open set U, for example, inside of here, then you can consider a ring that we could call RU hat. This is going to be something like meromorphic functions around U. So you can think of it as, you look at the regular functions on your model, which happen to be regular on U. And then inside of this ring, U itself is kind of represented as a prime ideal, which is kind of the closed fiber. And you can kind of U-adically complete that. So, and that's what these are. You could kind of think of these as like formal analogs of meromorphic functions around U. And at a point, you can look at the complete local ring, so I'm kind of completing it with respect to the prime corresponding to the point at P. These things behave kind of like an open cover. And there are overlaps, which are described in the following way. So kind of roughly speaking, if we have, let's say I have some U over here, and I have some P, which is kind of on the edge of my U. It might be somewhere inside here too, but it's, let's say it's, somewhere in the closure of U. Then what you can do is you can take the RP guy, maybe I should call it I should do it like this. You can look at the functions on RP hat, which are regular at U. So maybe this might just be the generic point of view or something like that if you're kind of just in the closure of it. But U still corresponds to you know, some locus inside of that guy. And then you can kind of U-atically complete that again. So this is kind of notation that doesn't quite make sense. To make it actually make a little bit more sense, we're really saying something like this. You can look at U. This is, let's say in the case where U doesn't include the point, where P is just in the closure. This is the typical case that we are interested in. And you can, so inside of the ring, the complete local ring at P, U defines, you know, U has some, U defines some codimension 1 closed set. And we, you know, and there are some primes. You know, if U maybe loops around or something like that, there might be more than one prime in that complete local ring, but you can choose one. And so for each prime P, we can consider what we could call R branch hat, which is what you do, you take RP hat, you localize at P, and then you, at the branch P, and then you periodically complete that. Okay. So, so in this kind of case that I've drawn over here, there are actually kind of two separate overlap fields going on. So if you, so if I look in the reduction graph, then we get these RPs and RUs for the vertices. So the U's are the complement of the P's in the closed fiber. The components of the complement of the P's in the closed fiber. And we have these branch fields representing the edges. So, if I had a picture that looked something like this, it's probably already too much to draw. You would have your X, your Y, your P, and these things connecting them are these branches, and then Y is connected to Q, is connected to Z, and Z is connected in two different ways to R. And you have branches for each of these edges, and these various R sub whatevers for the various components. Unfortunately, there's an R sub R there, but I'll try to ignore that. All right, so so you could call it some kind of formal patching. Says that we can construct algebraic structures over X via these RP hats, RU hats, and then the overlaps. And field patching due to Harbater, Hartmann, and myself, says that you can do the same for the fraction fields. So where Fp is the fraction field of Rp hat, Fu is the fraction field of Ru hat, with these overlaps to get structures over your semi-global field. Okay. So yeah, let me just see if I can get my slides to work again. I'll just this is really silly. There must be I just realized that some of them seem like they're missing. Yeah, there's like a bunch more slides that are missing somehow. They really were there a moment ago. It's really strange. Okay. All right. So yeah. So I need to say a bit about the how. And let me see if I can just. Yeah. Okay. So let's say how part one about the tori. Or I guess this is part two of the how, because the part one was about patching. The basic ingredients are that on the one hand, we have local global principles. For rational groups. So this is maybe a little bit of a hint as to why the R-equivalence stuff is happening. But in particular for tori, R-equivalence can be described via rational tori. So by the theory of Flask resolutions, if somebody gives you an algebraic torus T, you can find some other torus Q such that when you look at the image on field points, the image of Q inside of T is exactly the stuff that's R equivalent to 0. So whereas for some random reductive group, you don't know how to describe the R trivial elements very well. For a torus, they're described by some other group. And for this group, Q, we have local global. And this isn't really enough kind of by itself to quickly get that you can translate things to R equivalence, but it's kind of a big part of that. So so the process goes something like this. You might start asking about SHA with respect to some G. So G might be a torus or some other reductive group. And the first thing is that the formalism of patching, this thing that we can write torsors locally via this gluing information, says that, I mean, if you think about how this stuff works, it's really, well, okay, yeah. So what it ends up saying is that you can describe this SHA as a kind of combinatorial H1 with coming from this reduction graph with entries in what you might call, I don't know, G of F dot. So that is to say G of the F depending on the marking where you're at. So this is kind of like more of a coefficient system than kind of some fixed coefficient group. but this is the kind of description that patching kind of gives you. So this is relatively formal. More interestingly, we have this this kind of beautiful theory, which was worked out in large part by Philippe Gilles, which says that we can define these kind of specialization maps. And these specialization maps, oh wait, that's the next step in this process. Sorry, specialization maps are coming in just a moment. The first thing is just kind of via kind of a more direct homomorphism property. We can map this to these guys mod R. Really, the question is what information is lost here when you do that? And the magic is that, via, I guess, kind of like, I'm tempted to say homological, but it's really just by like a lot of kind of diagram chasing stuff, homological stuff. If G is a torus, you can get an isomorphism there. You kind of don't lose information. For a general root group, you might kind of lose some information going from here to there, but for a torus, it's an isomorphism. And then, as I was saying, via Philippe Gilles' theory, you can then specialize these guys and get stuff in these kind of fields of definition coefficients. So you get this kind of specialization map of this sort. Actually, that's not true exactly. You don't get a specialization map. There is a kind of, on the level of the coefficients, there's a map that kind of does something like that, but it's not. I guess there's a problem of it kind of being well defined when you say it like that, because part of this, it's well, okay, I'm not going to say it very well. In fact, what you get ends up being in the toral case, for example, as a surjective map going the other way. Okay, because basically the real difference within these things is the stuff that you're kind of is your kind of co-boundaries, the stuff that you're calling that you're kind of modding out by, and when you're just kind of modding out by things that are coming from constants, that's doing a lot less than modding out by things that are more globally defined functions. So it turns out that it's really the denominator that's kind of governing the direction of this arrow here. So this is again in the toral case. And this is via using Gilles' technology. Okay, so so altogether, what that tells you is that in the torus case, you then get, this is an isomorphism, and you get a surjection from here to there, and then the real result is that in the case of a monotonic tree, you can actually kind of combinatorially show that this coefficient system has to vanish, that this H1 group has to vanish. Okay, so and then in the case of in the case that the components are P1s over K, which is the residue of OK can in fact show that this is an isomorphism. So for that, I mean, the idea is kind of interesting. I guess the salient points end up being that how to say this, that so the tricky part, let me give you one kind of fun part of it, is that you want to be able to go between dealing with how to say this. So on the one hand, you're modding up by R-equivalence. On the other hand, this this H1 construction, you're modding out by things coming from the G of FUs and G of FPs, which then get mapped in different ways into the various G of F branches. And the main technical point is really to show that that these maps, where you're essentially taking a group element defined over some thickened curve and then restricting it to different points, don't have like a bigger image than if you just had a constant function on that whole curve and we're mapping it into these different points, at least when you're looking mod R-equivalence. And morally, the reason is that, well, if the curve in question was P1, then these different points were going to be R-equivalent because they're going to be connected by a rational curve. So it's the P1 of the components that's making this play nice with R-equivalence in the end of the day. Okay, that was not a very good explanation, but it is what it is. Okay, so let's now maybe say just a couple words about the more general. So this is all, so the torus is, is in the preprint. But then I'll say just a couple words about the reductive case, which is still in progress. And in which a slightly different kind of strategy is followed. So on the one hand, there is arguments of this sort which work just in one direction at least. So in fact, this statement about getting an isomorphism here in the case of P1s seems to still hold in the reductive case. So in the reductive case, it's not just about tori. You have that these guys are isomorphic. The problem is this isomorphism doesn't work anymore because this came from the fact that R-equivalence was described by these Flask resolutions. So the difference in the reductive case is that you get some map over here, but but it's hard to to say that much about it, except sometimes. Well, let's see. So it does appear that in the P1 case, this will still be an isomorphism if the P1s are all defined over the ground field. And in other cases, we can sometimes use this to at least show that that SHA is non-zero in certain cases, kind of give lower bounds for SHAs. Okay. So that's from the direction of we can sometimes compute the SHA and show that it's non-trivial. But the part that's a little bit different in the general reductive case is circumstances in which we can sometimes show that it is trivial. So I'll just say, just in a couple of minutes, so we have a different method for showing SHA equals 0 in certain cases. And that is, so if this reduction graph is a monotonic tree, then it turns out that that we can come close to making our class in in SHA FG, let's say it's represented by some, let's say explicit one co-cycle, for example, in here, a co-boundary. So we can almost use the combinatorics to get rid of it. The problem is we can't do it all the way, but we can, what can we do? We can change by a co-boundary. It's probably not the right way to say things when you're talking about non-abelian cohomology. It's not like there's really you're not modifying it by a co-boundary, but you're just changing its equivalence class, however you want to say it. We can find another representative of this class such that coming from, let's see, to come from, instead of Z1 of the reduction graph with coefficients in G of the Fs, we can make it come from G of the R hats. So you can kind of make the whole thing integral, such that if you specialize to the closed fiber, so all of these R hats are these rings where you can then mod out and go into the closed fiber. You get a trivial cocycle. So from that, if you combine with a kind of formal version of patching, so this was this is in in some work of Bastian Hasse, Lieblich, and myself. I'm in the middle there. Then you get a torsor over script X. So these things glue together to get something not just over the field, but something integral. Kind of as I was describing before, the kind of integral version of the patching, which is trivial along the closed fiber. So now we have like an integral torsor that's trivial on the closed fiber. And then via a recent result of Gilles Parimala Suresh, this torsor is actually Zariski trivial which tells us that our original torsor over F, because it's, it's what's going on Zariski locally, is also trivial, therefore. So this is the outline of the proof of this theorem, which was saying that, for G reductive over OK plus we got monotonic tree and mild hypotheses that I couldn't remember. We have that the SHA is equal to 0. Okay. All right. And I think that's about all I have. Kind of even more than I had on my slides, I guess, but that wasn't supposed to be the case. So, okay, well, thank you very much.
Thank you. Thank you. Thank you, speaker. Is there any question? Any question? Yes, please. Please switch on your mic and ask the question.
Yes. So this is Philippe. Yes, I have questions.
Yeah, sure.
Is the case SL1D very interesting in that your approach? I mean, what new does it said?
Yeah, so I mean, SL1D is a nice example because there are various well, because it's non-rational. So I mean, in various cases, so one can use it to get examples of where you have potentially large obstruction groups depending on the closed fiber. I mean, beyond that, I'm not sure if there's much in particular that we can say other than just that it contributes to examples that we now have. So I think prior to this, before we understood where SHA was coming from, it was totally unclear to us whether or not SHA was always finite, even or not, for any of these semi-global fields. And so because of the behavior of SL1D, we now understand that there's no reason it has to be finite, for example.
Okay, thank you.
Yeah, so more questions, more questions? Please switch on your mic and ask it. If there are more questions.
Yanni, what is known about finite groups in this setting?
Oh yeah, I should have mentioned that. So I think the finite groups were the kind of original reason that we kind of realized that there was interesting things happening with the kind of combinatorial topology of the closed fiber. So the main result is if you have, if G is finite, then SHA is this exact thing. It's it corresponds to G covers of the topological space, which is the underlying graph of that of the underlying reduction graph there. So yeah, so it's so there are whenever you have a loop, you have non-trivial SHAs, and that we can describe.
So more questions? More questions?
Can you hear me?
Yes.
Yes.
I have one comment, is that the one point about the reductive case is that this method enabled to give a counterexample in the case when the group is semi-simple, simply connected, which was an open question. So with an suitable SLD.
That's right. That's right. Yeah. Thanks for mentioning it. Right. Because it was certainly suspected, at least at various points, that maybe it was trivial, for simply connected. So, yeah.
I mean, the point is that in the number field case, this is a famous case where Xi is trivial. And one starts from the semi-simple, simply connected case with the triviality to get all the other results. Whereas in this setup, the information you have is for rational groups. And then there was a question whether for simply connected groups, the Xi was always trivial. And it was this whole method of getting this double coset and then this quotient, reducing ultimately to G of K mod R, which enabled us to get these counterexamples. And you should say that G of K mod R, which comes at the end, the fact that it's non-trivial, this goes back to Platonov's famous example.
Sure, sure.
Okay, that's all I want to say.